we can use superposition to predict what's going to happen when a wave interacts with a boundary. So the first thing we're going to consider is a fixed boundary. So here I have some wave moving towards the right. I am going to tie the end of this wave down. Let's say it's a wave on a string. I'm going to tie the end of that string down. Now, actually, let me tie it down a little bit closer. Tie it down right here. Now, the wave can't keep going on forever, right? It's going to hit that boundary, and then something's going to happen. What happens when that boundary is fixed? Well, I've got to conserve energy. Right? The energy of the wave can't just disappear. But we can imagine, this is going into imagination land, and it turns out that math world is a lot like imagination land, because we can treat this mathematically like the superposition of two waves in such a way that we're going to conserve energy. So we're going to imagine that over here, there's another wave. There's another wave that's going to interact with the first wave. The wave is just an inverted reflection of the incoming wave. So I'm going to call this the incident wave. I'm going to call this wave the reflected wave. Now, I'm drawing the reflected wave in a dotted line because it's not really there. It's imaginary. It's a ghost wave. It doesn't really show up until after the incident wave interacts with the boundary. But to the extent that the reflected wave, to the extent that we can treat the reflection as a superposition of two waves, we can imagine that there is a wave over on the other side, even though it's not really there. Okay, we're just imagining that it's there. Now, let's see what happens when the incident wave reaches that boundary. So, here's my incident wave. Now, my incident wave, I'm going to draw my incident wave with a dotted line now. My incident wave is pointing up and moving to the right. That's fine. Nothing bad there. My reflected wave is now right on top of the incident wave, however. When they are right on top of each other, remember my reflected wave is moving to the left. When they're right on top of each other, they're superimposed on top of each other. So while this wave is going up, this wave is going down. So right at this point, they cancel out, which is what I need them to do if my boundary is to remain fixed. If that is tied down so it can't go up or down, I want to make sure that these two exactly cancel out for all times right at that spot, because that spot is fixed. So at this point, the waves exactly cancel out, and my string is flat. Okay? Well, what happens after that? Well, after that, again I have my string, but my reflected wave keeps moving to the left. Whereas my incident wave keeps moving to the right. Now remember, it's not actually there. Anything to the right of the knot is ghost imaginary world. But what we can see, just using this, just using our imagination and using the fact that mathematically we can describe this reflection as the superposition of an incident wave and a reflected wave, we can see that the wave has to be inverted. The incoming wave points up, the outgoing wave, the reflected wave, has to point down. Whenever you have a fixed boundary, you have the incident wave in one polarization, the reflected wave is going to be in the opposite polarization. Now we're going to see what happens when I have an open boundary condition. By open, I mean the string is free to move up or down. The ends are not tied down. So, for example, we could imagine that I have a string with a wave coming down it, and at the end of the string there's a little ring attached to some pole, and the ring just slides up and down the pole. So it's not free, the ring is not tied down, it can move up and down. What's going to happen if we have this kind of open boundary condition, where the boundary is not fixed, it's not tied down? Well, let's see. Again, we're going to imagine that there is a reflected wave that's off to the side. However, this time I don't need to cancel out in the middle, so I don't need opposite polarizations. This ring is going to move up as soon as the wave hits it. So I'm going to imagine that my reflected wave has the same polarization. It's still pointing up, just like the incident wave was. Let's see what happens next. Well, at a certain point, is my reflected wave moving to the right, or left rather, my incident wave at a certain point is going to match up with the boundary. It's moving to the right. My reflected wave is also going to match up with the boundary, except it's moving to the left. If I take the superposition of those two waves together, I'm going to get twice the height, because it's just superposition. Superposition says that if I take two waves and I let them collide with each other, we get the sum of the two displacements. Now, no, remember, there's not really an incident wave and a reflected wave. It's just one string that's going up and down. But you can imagine that there's a reflected wave going to the left. Really what's happening is that all of the energy that is in the string as it's coming in gets transferred into the ring, and it gets picked up a whole bunch, even higher than it was before. If I wait a second later, my reflected wave is still moving to the left. And if we want to keep track of what our incident wave is doing, we can imagine that again it's passed off into imagination land. It's moving off to the right, as superposition would tell us it is. Now again, there's nothing really going on here. It's just a mathematical way of writing it. We can imagine it as the superposition of an incident and a reflected wave. Now we're going to examine what happens when I have an incident wave coming to a boundary, where the boundary is, it's tied to another string. So on the left, I have an incident wave coming in on a string, and the string is tied to another string, and as I've drawn it, it appears to be heavier. So I've got two strings of different masses. The heavier one is on the right. Now if I were to make this an extreme case, extremely heavy, like infinitely heavy, it would be like this string was just tied down. It would be like the fixed boundary condition. And if that's the case, we know we should get some reflected wave coming back. However, it's not quite that simple, because I do have to consider what's going on in the other end of the string. And the other end of the string is going to take some energy. The amount of energy that goes to the right into the heavier string is going to depend on what the ratio of the two masses are. So here's what we're going to do. We know the smaller mass per unit length is going to have a wave that's moving faster than the larger mass per unit length, the larger rope, just because the larger rope is harder to move. When do we do this? I could go out and derive the results for this. We'd have to match up the boundaries, take into account how fast the waves are moving. It's not that difficult, but it's a little bit messy. So instead, we're just going to logic our way through this. So I know this wave is heavier than the wave on the left. If it were infinitely heavy, I know that the reflected wave would be inverted. So that tells me that this wave should be inverted just because it's attached to something heavier. And the heavier wave, the transmitted wave, so we'll call this the reflected wave, call this the transmitted wave. Well, just by virtue of the fact that this one was polarized so that it was pointing up, I know the transmitted wave also has to be pointing up. However, the one difference is that this wave is moving noticeably slower, again, because we're going into a heavier medium. The heavier medium is harder to move. Therefore, the traveling wave through it is going to be moving slower. We can do the opposite case. I can have my heavy string hold the incident wave and have that be tied to a lighter mass string. Now, again, we could figure this out using math and try to match the boundary conditions and the velocity and the speed of the waves. We're not going to do that here. We're just going to try to logic our way through this. I have a very, very light string. Now, if this string were incredibly light, infinitely light, this would just be like the open boundary condition. It'd be like this wave, this big string was not tied down at all. Wouldn't even notice the tiny little string. In that case, we know that the reflected wave has to be polarized in the same direction. So my reflected wave would move back just a bit. Okay. However, not all of the energy would go into the reflected wave. So we know it has to be a little bit smaller than the incident wave. Some of it is going to be transmitted to the right, into the smaller string. Now, the smaller string has a smaller mass per unit length. We know that the velocity depends on how heavy the string is. And for smaller strings, it's going to have a faster velocity, which means that wave will have traveled a further distance. But in this case, my transmitted wave, it's going to be just like it was before. It is going to be, let me make the size a little more realistic. The transmitted wave is going to be further down because it is traveling at a faster speed. It's also going to be, I have to think about this, but I believe it is also going to be a bit wider because in the time it takes this wave to completely pass through that boundary, to hit that boundary, this one will have traveled an even further distance. So it's going to be a bit longer than the incident wave coming in. So we've got our incident wave, reflected wave, transmitted wave, passing through a boundary. We've gone from a dense medium to a thin, low mass medium. Now we're going to talk about something called standing waves. So imagine that I have two walls here and a string tied between the two walls. And let's say I pluck the string. If I pluck the string, I will have a wave. I can generate a wave by plucking the string that will go back and forth. And it will bounce back and forth between those two walls. What happens if the wavelength is comparable to the size, to the space between the walls? I'll call the space between the walls that distance L. What happens if my wavelength is comparable to that size? Well, turns out I can't just have any old wavelength. I have to match the boundaries. I know my string is tied down here and here. Therefore, only certain wavelengths will be able to fit between those two boundaries. Here's one of them. That's half, or excuse me, this is half of a wavelength. So we can say that lambda is twice as big as L is. To get the full wavelength, I have to go up once and down once. I've only gone up once, so I would need to go a distance of 2L to fit the whole wavelength in there. I could, alternatively, just as well, I could put one full wavelength so that lambda would equal L. And in fact, I'm going to write this a special way. I'm going to say that this is 2L divided by 2. The wavelength is 1L, lambda is L. I'm just going to put a 2 over 2 in there. In fact, I'm going to put a 2 over 1 in the first one. I'm doing that because there's a pattern that's going to build up. You'll see it pretty quickly. Here we go. Here's another one. Here's another way that I could fit a wavelength in here. I could go up once, down once, up once. Well, here my wavelength is 2/3 of the length of L. So we'd say lambda is 2/3 L, or 2L over 3. Now I should note that all of these waves, I've only drawn one mode of them, but really, there's another mode in there. Give myself more room to write that neatly. 1. And I can do the same thing over here. I can do one, I'll do one more here. I can keep going with this as long as I really like. Here's one full wavelength, 2 full wavelengths, so that lambda is 2L, or L over 2, excuse me. No. Yes, L over 2. L over 2, or equivalently 2L over 4. Again, I can do both polarities here. By now, you should have caught on to the pattern. I have 2L over 1, 2L over 2, 2L over 3, 2L over 4. Each time I go up, each time I add a new hump in the wave, my wavelength decreases by a certain amount. We can write that in a very general formula where we say wavelength n is equal to 2L divided by n. And sometimes I will call that the mode number of the wave. So we can talk about the first mode, the second mode, third mode, etc., etc. The particular wavelengths you get depend on the boundary conditions that you have. Notice that we have 2 fixed boundaries here. That won't always be the case. I could have had an open boundary here. That would change the types of wavelengths that I get, but the same process is in play. All we'd have to do is match up the boundaries and figure out what wavelengths could fit given those boundaries, and we'll get a different set of values for the wavelengths that can be stored. There are 2 types of important points on a standing wave. They're called nodes and antinodes. Points like this are called nodes. Nodes are the points on a standing wave that remain completely still. So while other points are bouncing up and down, my nodes stay fixed at one spot. The other important type of point on a standing wave is called the antinode. Antinodes are like these points right here. They're the points on a wave that are vibrating as much as possible. while the nodes stay fixed in one spot, the antinodes bounce up and down with as big an amplitude as possible. So, we've just calculated the allowed wavelengths for fixed boundary conditions. Fixed just means that both of these ends are fixed so that they can't move. We could do fixed open boundary conditions where one end is fixed and one of them is open. We could do open boundary conditions where both of the ends are open and free to move. In each case, you'll get slightly different values for the allowable wavelengths. We're going to stick with fixed for now, though. So I want to describe mathematically the shape of these waves. We can do that very similarly to how we did traveling waves. But we got to make sure we match on the boundary conditions. So we have y as a function of x and t. I'm going to label my boundaries here. I'll say this is x is 0. This is where x is L. So it must be true that my waves are 0. They have a height of 0 at each of these boundaries. So at x is 0 and at x is L, the height y should be 0. I can do that easily enough using a sine function. We can say that that's going to be the sine n pi x divided by L. That gives me the outline, the shape of the wave. And I'm guaranteed that if x is L, the only thing I am left with is n pi on the inside because the L's would cancel. And the sine of any integer times pi is going to be 0. If you look at your unit circle, the sine of 0 is 0, the sine of pi is 0. Any multiple of those will give me a sine that is 0. Now, this is only the maximum value that this sine wave can trace out. I also have to pay attention to the fact that these waves are not stationary, they're going up and down, they're oscillating constantly. So to do that, I need some frequency. So we're going to say that this is sine n pi x over L times the cosine of 2 pi times the frequency times the period. It's undergoing simple harmonic oscillation. We called the boingy motion before. Each point on these waves are oscillating, so that my wave is going down on one side and going up on the other side. This equation accurately describes that motion. Now, how do I find the frequency? Well, we know the wavelength. If I know the wavelength, I can find this frequency. The frequency is also going to depend on n. The wavelength depends on n. The frequency depends on n. The frequency is, as always, just the wave speed divided by the wavelength. Okay, so how are standing waves related to traveling waves? Well, it turns out that a standing wave is actually two traveling waves in disguise, which I'm going to show you in a minute. For now, here's some code that produces a standing wave, but it does it by animating two traveling waves. This is just proof of concept. So let's pay attention to this line right here. So this is the equation for two traveling waves. We can see that one of the waves is a left-moving wave and one of the waves is a right-moving wave. I can see that because one of the signs in the cosine function is negative, while the other sign is a positive sign. So I know the negative one moves to the right, the positive one moves to the left. I'm also going to plot my two individual traveling waves. So we'll be able to see the two individual traveling waves and then the superposition, the sum of the two of them together. So let's go ahead and run that. We can see, just like my Mathematica code before, I have to increase the wavelength to be able to see anything. I have to increase the amplitude. and I have to increase the period so that it doesn't go too fast. Let's try animating this. We can see a red traveling wave moving to the left, a blue traveling wave moving to the right. The black wave is the superposition of the two. Now, we notice the black wave is a standing wave. It's just moving up and down. It doesn't appear to be traveling anywhere. Now, we can try adjusting the time here, and we can see at this point that my red wave is 180 degrees out of phase with my blue wave, which is why the black wave is exactly canceled out at that time. Now, if I move just a little forward in time, eventually the red and the blue wave will align again, and at this point my black wave will be at its maximum. We'll see the peaks get as big as they're possibly going to get, the valleys will get as low as they're possibly going to get. This is because the red and the blue waves are just adding together through superposition. So standing waves sure look like they're the superposition of two traveling waves, but is there a way we can show that mathematically? It turns out there is. I'm not going to do it in this video. All you have to do is look at the sum and difference formulas for sines and cosines. And if you do that, you should be able to prove pretty quickly that a standing wave really is two traveling waves. And it's not that surprising that it should be, right? If I think about what a standing wave is, all it is a wave where the wavelength is big enough that it's larger than the space that it can fit in. So you can imagine that wave is bouncing back and forth, reflecting at the boundaries. And as it reflects at the boundaries, it's like I have two traveling waves going in opposite directions, constantly reflecting off the boundaries and interfering with each other.